Dear learners, welcome to week 3 lecture 2. In this lecture, I will cover that cell governing equations. Already we have obtained in lecture 1 of week 3. Now we will discuss in more details and the associated boundary conditions. So, we shall derive that set of governing equations in the I think last week lecture or lecture 1 of week 3. I have covered that kinetic energy, internal work done and derive the relations of external work done. Now, I am clubbing all the terms together and equating it to 0. So, as per the Hamilton principle, the first variation in kinetic energy minus of potential energy, where it will contain two contribution, that first one is corresponding to internal work done and second one is corresponding to external work done. So, internal work done is nothing but basically that strain energy of elastic body. So, if we club all these equations, basically contribution of kinetic energy, contribution of strain energy and contribution of external work done. So, this is the contribution of kinetic energy, this is the contribution of external work done and this is the contribution of internal work done having linear contribution, and this is the non-linear contribution. Here you see that all are having del u10 coefficient. So, basically we have clubbed del u10 coefficient at one place, kinetic energy, external work done and internal work done. Okay, I have write that 0 to t integration, area integration is inside and yes, definitely outside and that is going to be 0 plus the contribution, that coefficient of del u20. So, del u20 will have these terms and non-linear terms, these two terms plus kinetic energy plus extension work done and then coefficient of del psi 1. In the del psi 1 there is non-linear terms and kinetic energy, and under this head we do not have even the external work done. And then this is the coefficient of del psi naught and contribution of kinetic energy, and these are the coefficient of del w0, that q1a2 and q2a1 and kinetic energy and external work done, plus these have contribution of non-linear. Now, we can say that we have clubbed all the equations at one place and integration from 0 to t, and these del u10, del u20, del psi 1, del psi 2 and del w naught are arbitrary variation and their coefficients are integrable over the range, basically alpha 1 to alpha 2. So, definitely we can use the fundamental theorem of variational principle, which we call it fundamental lemma of variational principle. So, if we use that one, so these are arbitrary, so this coefficient must vanish. So, this will lead to or help us to get ordinary differential equations. So, we will get 5 ordinary differential equation, let us say equation 1, equation 2, equation 3, equation 4, equation 5. In some of the shell theories book, that equation 3rd and 4th kept at the bottom, in some of the theories it is kept in between. Here we can see that all equations are coupled, like you see that this term Q1, Q2 is in equation 5, Q1 is equation 3, equation 4, equation 2 and equation 1. So, they are coupled through this shear, and if we consider the nonlinear terms, so through nonlinear also first, second and fifth equations are coupled together. I would like to point it out here that if you talk about a plate equation, just I am going to write for a rectangular plate nx comma x plus nx y comma y, let us say for a static case, then nx y comma x plus ny y comma y equal to 0. And third equation, if you talk about classical plate, double derivative plus mixed derivative plus let us say Q3 loading. So, here that these in plane equations are not coupled through third equation, that moments equations are not here, or if you write in terms of FSDT, here Q1, Q2 do not come. So, we can solve these two equations independently and third equation independently, but for the case of shell it is not true. They are coupled through Q1, Q2. So, we cannot solve independently, we cannot say that we solve only the third, fourth and fifth equation together and 1 and 2 remains. No, they will affect 1 and 2. Basically, in the shell, if a shell is thin, that a small, even the bending effect or a bending force may cause extension, means stretching, large stretching, significant stretching. In the plate it is not so. So, this is the first observation, and second observation is that we can take consideration of nonlinear terms, means without nonlinear terms we can consider generally that thin shell theories nonlinear terms are not considered, they are linear one. So, this is the standard general equations, and again if a shell is symmetric, that I1, where I1 is inertia, mass moment of inertia, it is going from minus h by 2 to plus h by 2 rho times zeta 1 plus zeta by r1 and 1 plus zeta by r2 and dg. So, for a symmetric it gives a value of, so if we talk about a thin shell, in the thin shell these terms are neglected, whether if you take about Sanders theory or Love-Kirchhoff shells or the person. So, generally they do not consider this effect because thickness is small and radius is very large. So, it compared to 1 these are negligible. So, this I1 can be 0, but if you talk about a thick shell then definitely it will have some contribution. In other way, if you talk about a plate, for the plate case I1 is always 0, whether plate is thin or a thick, for a symmetric plate. So, in the case of shell it is not 0. So, that is why we have kept I1 here. Here that you see that small q1 a1 a2, here a1 a2, here a1 a2. So, in most of the books this A1 A2 will be taken common out. So, if we take common out, then this governing equation looks like this, that 1 upon A1 A2 and linear portion plus Q1 by A1 non-linear portion plus already A1 is, because A2 was there, so it will get cancelled out. So, A1 R1, A2 R2, and loading term will not contain A1 A2, and similarly dynamic term will not contain A1 A2. So, in the book Theory of Cells, you will find the final form of governing equation like this. Previous set of equations was the intermediate part just after the integration. So, we find that these are A1 A2, where A1 A2 are the Lamé parameters. So, this is the exact form which is represented by in various textbook, taking one A1 by A2. So, anyway, if we want to work with this, we can work on it. So, we have 5 governing equations. Now, we move to the boundary conditions. So, in lecture 1 of week 3, already this portion was there, that contribution due to I1, and this is contribution due to I2, and this is the contribution due to I3, then I4 and I5. So, we are having a contribution like this. Here slight correction is there, it should be that beta 1 to beta 2 or alpha 1 to alpha 2, that is more consistent compared to writing 0 to alpha or 0 to beta. The reason behind that theta, it can take any value. So, it is not necessary to start from the 0. So, we are saying it can be anything. So, maybe you say that 0 to 30 degree, or you say that 30 degree to 60 degree, between that some component is there of volume element you have taken. And these are the contribution of from the edge work. And the contribution from the edge 2, WE2, WE1. So, we are put it together and equate it to 0. Ultimately, that area integral plus boundary integral going to be 0, definitely time will come up here. So, overall I am going to put integration 0 to t, and at the end dt equal to 0. Or t1 to t2. I would, before proceeding further, I would like to say that, let us say we have a term like 0 to t is final integration over, inside that let us say a, integration of b, integration of c, integration of d, and dt is going to be 0. So, we will say that all individual integration to satisfy this need to be 0, okay. That is first thing, that this integration d alpha is going to be 0, this integration d beta is going to be 0, and so on. Now, again inside this a, we have a term, let us say a1 b1, a2 b2, a3 b3, and d alpha, let us say. Now, we will say that to satisfy this equation individually, that each term need to be 0. So, we first here like integration from beta to this one. So, we will club together all integration which are from under d alpha line and under d beta. So, these terms will go to here d beta and these terms will go to d alpha, again this also. So, if we club all the terms under one head, that edge along beta edge and alpha edge. So, if we do so and collect all the terms under alpha and under beta. So, basically the first one, the boundaries are associated where beta is constant, beta 1 to beta 2, and the second integral is related to where alpha is constant. Means if we have a patch like this and we are always saying this is our alpha, this is our beta. So, let us say alpha is equal to alpha 1 and alpha is equal to alpha 2. So, this is the edge where alpha is constant. So, over these edges these conditions will be satisfied, and this edge basically let us say beta is equal to beta 1, beta is equal to beta 2. It may be 0 because you have taken the coordinate system here itself. So, it will be 0. So, this will be the edge where betas are constant. So, these variables need to be satisfied. So, I have already told you that we are going to putting this term individually 0, this term individually 0, this term individually 0 and so on, and del W naught coefficients. So, if we do so, we will get a edge where beta is constant, either or conditions are there, either this or this, either N2 to A1 or U to 0. Sometimes we can say prescribed. The very reason to write like this, we are not saying that N2 to is 0, no, we are saying A1 will get cancelled out from both sides. You can right now cancel it out, or you can take it as it is also, there is no problem. That N2 will be equal to applied N2. So, an edge, if this is, maybe you may say that I have applied N2, the external in plane resultant, then at the boundary the internal stress resultant N2 will be equal to N bar 22. Same way at the boundary the displacement U20 will be equal to external applied displacement. This may be 0, may not be 0. So, it is not necessary that it is 0. So, we should write in a more general form. And the second reason to put this A1 here, for present case you may get cancelled out, but there are some cases where you say that boundary is free. If we talk about a circular plate, then it will be N22 of R is going to be 0, not just N22. So, then you may ask that from where this R is coming. So, basically this is A1. So, that is why I have kept A1 is here, because they are in the terms, but anyway one can get, they will get cancelled out. So, in first case N22 or U20, N21 or U10, M22 or psi 2, M21 or psi 1 or Q21 plus this nonlinear contribution equal to Q2A1 or W0. So, we have to choose, these are the 5 variables at one edge. So, only out of these variables we have to choose on the edge where beta is constant, and another edge where alpha is constant, we have another 5 variables. So, there either N12 or U20. Again I would like to say that U20 of bar, applied one, normal stress resultant N11 or U10 or M11 or psi 1, then Q1A1 and Q1A2. So, these are the cases are applicable when your geometry and coordinate axes are matching. For example, you have taken boundaries like this and your variables are also like this, alpha and beta. So, that normal and tangents are along the same coordinate axis. But there may be cases where you have chosen a coordinate system some like that, but we are getting a boundary like this, a corner like this. Instead of this, we are getting a curved shape. Then over these boundaries, what are the variables to be specified? So, at the boundaries, we have to say in terms of tangent and normal. So, I am going to write these variables in terms of tangent and normals. So, NN normal to that edge or UN0, NS, or sometimes instead of writing it like this, you can say that U0N, or you are writing that U10. So, UN0 is fine, then US0, because we are saying U20, then QN, W0, MNN, moment in normal, then psi n, then MNS, shear moment or coupled twisting moment, and psi t. So, now we say that if n is your alpha, then t will be your beta. Then you can directly map, okay, these are this thing. If n is your alpha is 1, then it will be N11, N12, Q1, M11, M12. If that normal is your beta, then you can find out rest of the variable. So, it is better to write in a more general sense, so that depending upon the requirement, you can convert into the explicit form. Now, I am coming to the very first shell theory, that Love-Kirchhoff shell theory, and in that theory gamma 2,3 and gamma 1,3 are neglected, and then epsilon 3,3 also neglected, based on the assumptions that transverse axis remains perpendicular to the reference surface before and after the deformation. There is no change, basically angle remains 90 degree. So, if we pose those constraints, then your rotations will be a known one in terms of in plane deformation and transverse displacement. Similarly, psi 2 is known to you. Then if you know all these things, so whatever we get now 5 differential equation, that can be converted using this concept into 3. Same way you see here that at an edge we need 4 boundary conditions, that we will have 4 variables U10, U20, and one will be a slope and W0. So, first of all we need to modify the boundary conditions so that we will get these 4 variables. Already I have said that if you apply law of Kirchhoff's assumptions, it will be 8 order PDE, partial differential equation. So, we can satisfy maximum or we can solve 8 variables. So, we need 8 boundary conditions. So, for the case of FSDT, we have 10 boundary conditions, but in the classical shell theory, sometimes we called it CST, classical shell theory, it will have 8 boundary conditions. So, for that purpose, we have to modify the boundary conditions. So, what are the variables we are going to modify? So, basically if you that these two, right now I am doing without nonlinear terms so that it will be easy to explain, but if you include the nonlinear term, definitely one can proceed with that also. So, for explanation point of view, in this case I have deleted the nonlinear terms and I am proceeding further. So, that is the edge where beta is constant, edge where alpha is constant. So, in this edge m2 to psi 2, basically let us say rotation and del psi 1. So, it is integration along the alpha. So, this term need to be modified. This is fine, this is fine, this is fine. So, this term need to be modified. It is basically rotation. When we are talking about in second direction, so rotation will be in that axis. We do not need this one, it is fine. If we substitute that value of del psi 1, so del psi 1 is this one. So, if we put del u r 0 1 by a del w comma alpha. So, one term will give contribution to the del u 1 0. So, r 1 comes inside. The second term will give you the contribution to the del w naught, but again it is derivative with respect to alpha. So, we will further reduce it to just del w naught. So, if we proceed further, it will give you 2 terms, one is this, second is this. So, this term if you integrate, it will go to the corner and it will look like this, that m21 minus m2 bar del w naught alpha 1 to alpha 2 and beta 1 to beta 2, ये आपका contribution है. Generally, we do this derivation before adding our external work done. Then this term will go to the contribution of del w naught. So, del w naught has this q2 contribution and del u naught contribution as n21, and this is known as Kirchhoff shear corner terms. That now the boundary condition will be either n22 or u20. Then next combination will be n21 plus m21 by r1, a club term. So, it is generally expressed like T n21 plus u. Third remains same. In the fourth we add m21 derivative with respect to alpha, a1 is here. So, divided by a1. So, q bar 1 m21 comma alpha or w naught, and this term is known as Kirchhoff shear Vn or V1. So, if I write in terms of n and t, it will be nn, t and t, Vn and m1, where t and t can be written like this. For the case of a plate, r is infinity, so it will be equal to nt, and Vn will be Qn 1 upon mnt even alpha t. So, we have converted 5 boundary variable to 4 boundary variable using the concept of that psi 1 or psi 2 is expressed in terms of u1 0 by r minus 1 over a1 del w comma alpha or alpha 2 something. Same way one can go for that edge where alpha is constant, then you have to psi 2 you have to consider psi 1 remains same. So, in this way that edge where alpha is constant, the variables will be find out. Now, we have a various support conditions. If we say that if a edge is free, then our natural variables, sometimes stress variables are also known as natural variables, and these variables are known as essential or kinematic variables. So, in plane stress resultant, TNT, shear force, MNN is going to be 0. If a edge is clamped, then all 3 displacement plus rotation is going to be 0. Simply supported boundary condition is a mixed type boundary condition, and in this we find a number of that movable simply supported, immovable simply supported. Sometimes there is another classification that hard simply supported and soft simply supported concept. So, if we talk about a movable concept, that a normal resultant NN, TNT is going to be 0 and deflection and moment. So, generally deflection and moment is fixed, that deflection, transverse deflection is going to be 0 and normal moment couple is going to be 0. But these two variables we change with that. So, if we say that instead of normal stress resultant, if un 0 and instead of TNT u2 is 0, then this type of a boundary condition is known as immovable boundary condition. If we say that instead of a TNT, let us say another setup that NN is 0, that is final. Instead of a TNT, I said that u2 is 0, then w is 0, then MNN 0. So, if we choose the variable like this, it is known as hard simply supported, and most of the cases analytical solutions are available for hard simply supported boundary condition, and this type of boundary conditions are also known as soft simply supported boundary conditions. Already immovable concept is given here. So, we can choose from the variables that which are going to be specified. Now, a small concept also there, that if we talk about a thin shell, very thin shell. So, zeta by r1 and zeta by r2 can be neglected. If this is the condition, then our n12 will be equal to n21. Here I would like to again tell you the definition of n12 is tau 12 1 plus zeta by r2 and integration over zeta and d zeta. Then n21 is the definition, by definition is 1 2 or 2 1 you can write, say no problem, 1 plus zeta by r1 and d zeta. So, n12 is not equal to n21 because of this term zeta by r12, tau 12 equal to tau 21, but these terms are not same. If we say that shell is very thin, then this can be neglected, and in that case N12 equal to N21. Same way M2 equal to M21, M12. So, this is the sixth equilibrium equation exists for the case of thin cells. If we are talking about a thick or moderately thick, this concept is not required, that the previous differential equations are valid. But if you want to say that I am going to analyze very thin shell, then we need a correction terms, because we do not get this equation. So, we say that by vanishing moment about the normal to the reference element, that this is going to be 0. In this equation, this term, or first of all I would like to say that this is the sixth equation and it cannot be obtained from the Hamilton principle, because it is an identity. If we say that this concept N21 minus N2, if you want to write in that form, that is going to be 0. So, most of the cases when we have a spherical cell where R1 equal to R2, then this equation is identically satisfied, equal to 0. When we say it is a flat plate, then this equation is also satisfied. And if we say that shell is symmetrically loaded, in that case shear components is always 0, that shear resultant in plane displacement and couple is going to be 0. So, we have proved that already it has been established in the literature, in the books, that N21 minus N21 vanishes in every case, but this term may exist, this may be small. So, we need a correcting term is introduced into the first two equations, जो हमारी basic governing equations है number 1 and number 2, उसमें हमको कुछ correcting terms add करनी है, and the procedure is given in most of the thin shell theory books. So, I have just written that what is that extra term is included. So, detailed derivation one can see a very recent book by Jane Reddy, or in the Harry Carus book it is also there, and in other shell theories book also. So, M12 now it is denoted by tilde, because they are same now, zeta by tau 12. So, here C naught is a constant 1 by 2, 1 by R1 minus 1 by R2. So, if you multiply with it, and it will contribute to del U10. So, C naught A1 M12 comma beta will be added in first equation. Similarly, in the second equation it is that 1-2 derivative comma alpha with the minus sign. So, if we do these corrections, then the exact form of Sanders shell theory is obtained. But this correction is required only for thin shells. If we are interested to moderately thick shells or thick shells, then the previous 5 equations are completely valid. Now, we talk about the boundary conditions. Already we have discussed that we should specify stress resultant, moments, in plane displacement, rotations, but where? Because in a shell, in a plate or a beam, it is clear cut case, there are open boundaries. If you talk about a plate, if you talk about a beam, there are boundaries are available, but in the case of shell it is not true. If you talk about a complete closed cell, let us talk a sphere, then where do you provide the boundary conditions? There is no open end. Similarly, a cylindrical shell, completely closed cell, then also it is difficult. So, the previous set of applicables when you have a both ends means at corners are available for the boundaries. So, in the boundary conditions, if a shell has no boundaries, it is completely closed. The coordinate lines alpha and beta on the middle surface of the closed shell will be closed. They will not be free, open. So, concept of boundary condition loses its meaning. So, in case of complete or closed cell, the boundary conditions are replaced by the condition of periodicity, means you have to in a periodic manner satisfy the boundary conditions. Symmetric concept basically. A cell is closed with respect to one coordinate and open with respect to another coordinate. Then we can apply where the coordinates are closed, the condition of periodicity will be applied, and which coordinate the shell is open, then we apply the regular boundary conditions which are we have obtained. So, this type of information is given in a book, Thin Pattern Shell Theory, Analysis and Applications by Theodor Karuthamar and Eduard Wenzel. So, in that book I think chapter 10 or 11 is devoted to the shell. Next, a shell is open. Yes, it is perfect to work with this both coordinates like panels. So, we can say that sometimes you find in literature that a shell panel is solved instead of a closed shell. So, most of the applications in structural applications we like when we talk about aeroplane wing or so they will be like a panel kind of approach, shell panels or your roof of any structure. If it is a closed like a spherical dome, then it is different. But if these days you see that roof of metro stations or a roof of a parking lot or a roof of any garden or that greenhouse gardens roof. So, they are having this kind of panel kind of system. So, you can apply on both edges following boundary conditions. Already we have discussed that as where alpha is constant. So, basically when this is your beta, beta is increasing over this S over this line, beta is going to be constant. So, normal will be beta and over this line alpha is constant here on this line. So, one can specify the boundary conditions. Next, that in the Kirchhoff shell theory, I have already told you that we can obtain law of Kirchhoff shell theory by substituting the expression. So, from this equation we will get Q1 and from this equation we will get Q2. So, by carefully you say that multiplying with A2 and differentiating with alpha and differentiating with beta and putting it here give you the third equation, and same way substitute the value of Q1 by R1 here and Q2 by R2 here. So, we will get 3 equations. So, those 3 equations will be valid for CST, classical shell theory. So, these shell equations are available with us, but can we work with this? Can we get the solution just by solving these equations? No, we have to first convert to the main primary variables. What are our primary variables? U1 0, U2 0, W naught, psi 1 and psi 2. So, we have to convert this set of equations into these primary equations, then only we can solve it. So, even till date solution of these equations are very difficult. Why it is difficult? You see that these are the partial differential equation with variable coefficient. Here the coefficients are varying with respect to alpha and beta. So, this R2, you have some coordinate system R1 and R2, not radius of that, and you are taking differentiation of this. So, A1, A2. So, these are the PDE with variable coefficient. So, which are difficult to handle. So, from the day started when the first shell theory was proposed, since then that we have specialized development or solution techniques, like I am going to like say we have developed a general shell theory, and now I am saying that let us say a shell is subjected to only membrane loading or a membrane shell theory. So, lot of application in the industry where shell is acting as a membrane. So, it is not taking any transverse loading or bending loads, and there are some applications where it will takes the flexural bending. So, shell under flexural bending, and there are some where we have some axis symmetric loading. By doing so, one by one, some terms get eliminated and solutions becomes easy. So, in the directions I am saying that types of state of stress for thin shell, like membrane theory of cells. So, effect of bending and twisting is neglected in this theory. So, basically a hollow spherical cell subjected to inside and outside uniform pressure. So, then it will be covered under a membrane theory of shells. Then we have a case of pure bending or flexural state of stress. Some studies has been done or the equations are solved, but this for a actual physical point of view, this condition is very dangerous, because a small bending in bending and stretching cannot be decoupled. If there is bending, definitely there will be some stretching effect will be there. So, then the mixed case, which will be, I would like to say that for more complicated one, and then the case of axis symmetry, then the loading. Because of the loading also the equations get simplified, skew symmetric and symmetric, even till date that most generalized shell is not solved. They are mostly regular cells, which we called it like revolution of surfaces, like cylindrical shells, spherical shells. The structures are made out of that. So, 90% literature or books that cylindrical shells, conical cells and spherical cells basically are solved, which are, I would like to say that governing equations slightly less complex, but the other cells which may have completely different profile or doubly curved, and those type of shells, even till date cell equations are difficult to solve. So, further in the next lecture I will drive that can we get the equations for a plate, cylindrical shell, spherical cell for the given governing equations. So, first we will try to find out that can we get from this our governing differential equations, that special cases. I will explain that first and then we will proceed further. Thank you very much.